Hey everyone, my name is Keshav. I'm here to talk about our work on investigating exploration for deep reinforcement learning of concentric tube robot control on behalf of my fellow authors here at IPCAI 2020 in conjunction with CARS. If you have any comments or questions, please don't hesitate to contact me at my email listed below. So a good place to start is what concentric tube robots are. So concentric tube robots are these pre-curved, super-elastic, telescopic nitinol tubes with a small diameter footprint. And as the tubes rotate and translate relative to each other, you can create these curvilinear paths. And one proposed application for concentric tube robots is that of fetal surgery. For example, in twin-to-twin transfusion syndrome, rather than using these rigid instruments, we can use concentric tube robots for their flexible articulation. They minimize the incision point, and they still offer dexterity at the tip. So the goal of our paper is looking at how do we get the rotation and translation for each tube if we want to achieve a certain robot tip Cartesian goal position. So some prior work on concentric tube robots has been around Costa rod modeling, where the tubes are represented as deformable rods with a certain stiffness matrix. However, this approach can result in some errors in manufacturing inconsistencies due to the nitinol manufacturing, as well as unmodeled tube interactions like friction. So Grassman presented a paper looking at multi-layer perceptron networks in a 3-tube concentric tube robot system to do the forward and inverse kinematics, and did so with pretty good results. And we directly used their trigonometric representation used in that paper. So here alpha is the rotation and beta is the extension per tube. And an important thing here is the constraints on beta to make sure from the actuator side of things that the extension is actually possible. So going over reinforcement learning, one of the benefits is that we can iteratively go from simple environments to complex environments and then eventually to hardware environments with things like sim to real and transfer learning. And so this can be data efficient if the cost of collecting real hardware samples is expensive. So how reinforcement learning works is basically we have an agent and we have an environment, and the agent provides an action to the environment. The environment then simulates one step with the action and returns to the agent a state and a reward. And the goal of the agent is to come up with the next best action to have the greatest cumulative reward, and this can be done with a policy pi given a state and then theta of the parameters of the network. In reinforcement learning, there's a concept of episodes where the agent has a number of time steps to interact with the environment before the environment is reset in some manner. And so there's also a critic which takes a state and an action and estimates how much this cumulative reward is going to be by the end of the episode. And so there's this interdependent nature between the policy and then the Q value or the Q function, and this results in the actor-critic methods. And the general idea is to use the policy gradients to move the policy in the direction best suggested by the critic. So one of the things in reinforcement learning is we need to come up with a Markov decision process, which consists of a state, an action, and a reward definition. And so our state is just going to be our trigonometric representation for each tube, the desired Cartesian goal and the achieved Cartesian goal. The actions are going to be changes in rotation alpha and extension beta per tube. And the reward is going to simply be 0 if our error is below a certain threshold, or -1 if it's greater than some threshold. We chose to go with this -1 to try to limit the number of unnecessary steps in the episode. So the specific actor-critic method we chose to go with was deep deterministic policy gradient for its stability with respect to hyperparameters and the fact that it's off policy, which is a requirement for exploration. So our policy network looks like this. We have our states, which are just the trig representations for each tube with the achieved goal and desired goal. We have 3 hidden layers of 128 nodes each, and our outputs, which are the actions. We also used hindsight experience replay, which is important because we're using sparse rewards of 0 and -1. And so the basic idea is that at the beginning of an episode, say we have our achieved goal at the black dot and our desired goal as the green dot, and we through the episode we end up with the second point, the second black dot, and that line represents the trajectory that is taken, or the state, action, reward at each time step. The idea of hindsight experience replay is we say it was not the original desired goal, but in fact the place that we got the achieved goal at the end, that was the original desired goal. And we can do this because we can back propagate the desired goal all the way back through the trajectories back to the original black dot. So for simulation, we went with the dominant stiffness model for concentric tube robots, which assumes that the outer tube is much stiffer than the inner tube and is what determines what the overall curvature will be for that segment. This model is quite simple, but it works well enough for our exploration investigation. And with the dominant stiffness model, we can do forward kinematics. So given the rotation and translation of each tube, we can determine what the achieved goal is, or the robot tip position at any given time step. And at the start of every episode, we need to determine what the new desired goal is going to be. So we do that by uniformly sampling through the joint space, making sure that they're within the constraints of extension, and doing the forward kinematics to determine what that Cartesian desired goal is going to be. And in the workspace, we see that with larger number of tubes, there's more degrees of freedom, the workspace becomes larger, and also there's more redundant solutions. So rather than plot learning curves, I thought it would be interesting to see what the exploration strategies actually look like. So here we're plotting the achieved goal points along with their associated Q values normalized between 0 and 1. And this is for the 2-tube single variate noise experiment, where single variate just means that we're applying the same variance to both extension and rotation actions. Here we're doing for Ornstein-Uhlenbeck noise, where we were mean varying throughout the time steps to push for extension, as well as we separate out the rotation and extension variance in a multivariate way. So what we see here is that because the critic is poor at estimating Q values in the single variate case, we see a homogeneous set of Q values, whereas in the Ornstein-Uhlenbeck case, the critic has become fairly good at estimating Q values, so we see a more diverse set of Q values, which makes sense because depending on state and desired goals, we can get different Q values. So now what we can do is take a slice about the XZ axis, and what we see is that the single variate noise, even from 25 to 100%, still struggles to reach the full extension, versus the Ornstein-Uhlenbeck noise can really stretch out and push towards extension because of that mean varying property. So because the desired goal is actually within the state, what we can do is change that desired goal through the time steps and do some trajectory following. And so what we do here is at a high extension value, we try to follow a square trajectory on the XY plane for the single variate and the Ornstein-Uhlenbeck noise. And what we see is the single variate really struggles to follow the square trajectory, versus the Ornstein-Uhlenbeck can follow the trajectory quite well. And with that, I'd like to conclude my presentation by offering some future work. So we'd like to focus more on bringing this to hardware with things like sim-to-real and transfer learning by making the policy more robust, and that starts off by using a more complex simulation environment rather than the dominant stiffness model. And if you have any questions or feedback, please feel free to reach out.